ahead and hit record here. So welcome this morning. I hope everyone is doing well out there. I want to start by talking about something that I posted yesterday for everyone. So if we're looking at Canvas together real quick, I posted, if you go to assignments and find exam 1, I posted the review guide for exam 1. All the details that you need, it'll be next Friday in class. So rather than do our online Q&A next Friday, we'll meet in class and take the exam. I've got all the topics for review here, including questions out of the chapter review in the textbook that correspond to the kinds of things that I'm holding you responsible for. Anything that's highlighted in red are things that you should memorize, like definitions, maybe a list of, the ways a function can be discontinuous. We're going to introduce a new list today, a list of how a function can be not differentiable. And then the 2 limit formulas that we've talked about in class, you need to memorize those as well, the limit formulas for the derivative. But having said all that information is there. I've tried to condense it a little bit so that you're not just studying everything. But these are the topics that you'll be asked to be prepared for the exam next Friday. You do not have any homework due tonight. Normally the homework is due on Friday night, but since this is a 2-week module with an exam at the end of it, your homework's going to be due on Monday night. So we'll cover the last thing that we need for this particular section on Monday. And then probably Wednesday of next week, we'll start looking at stuff that's going to come up after the test. So we may review a little bit next Wednesday as well. But your homework will be due on Monday night of this next week. You'll still have your skills quiz due next Wednesday, like all the skills quizzes have been. So do y'all have any questions about the exam, the timing, anything like that?
Our skill quizzes due when for chapter 3?
It's due next Wednesday, just like normal.
I got you, just checking.
Yep. I'll probably bring this up again at the beginning of class on Monday. So if you look over things and you have any questions for me, feel free to bring them up on Monday. All right, so with that out of the way, let's chat about today's topic, which is going to be differentiability. There are going to be some Q&A parts of this, but there are also going to be some lecture parts of this today. So today's a little bit different than the last 3 have been. But I want to start with a question that, as a follow-up to the very last problem that we did in class together on Wednesday. Remember, we were talking about the balloon being blown up, and we were trying to determine the rate of change of the balloon's volume, given that the radius was expanding as we blew up the balloon. And we talked a little bit about units and things like that. And I just want to follow up on that and make sure that we understand what the derivative is telling us for a given problem. So if you are logged into Learning Catalytics this morning, go ahead and try this particular problem. I'm outlining a certain cost function here that we've taken the derivative of. So in business, anytime you take the derivative of a quantity, it's usually called the marginal version of that quantity. So the derivative of profit would be marginal profit. The derivative of revenue would be marginal revenue. In this case, the derivative of cost is marginal cost. So the marginal cost is given by this function. And if we plug in 500 to this function, we get 15. So what this question is asking you is, what does 15 mean in the context of this problem? In other words, what is the derivative trying to tell me on this example? So take a look at it. Tell me what you think. All right, you got about 30 more seconds to respond. All right, all the answers are in for those of you that are logged in right now. I'm glad we're talking about this. The correct answer here is B. Let's talk about why. So if you recall at the end of class last time, we were looking at the balloon. So you blow air into the balloon, it increases the radius. So the radius of the balloon was increasing. So we called that delta R was that increase, and it led to a delta V increase for the balloon as a whole. So what we did, if you recall, was we found the limit as delta R goes to 0 of delta V over delta R, which we call dV/dr in class. So that's the derivative of volume with respect to radius. And we said that that was 201.1 inches cubed per inch when the radius was 4. So that's what we left class with on Wednesday. And I wrote up on the board, or when we were talking about this, I wrote up on the screen and said, you know, or asked, what does this number mean in context? We were talking about the different possible interpretations of the units here, inches cubed per inch versus inches squared. And I said inches cubed per inch means that the expected increase of the volume when the radius is 4 inches is 201.1 inches cubed per inch. Now understand what that means. That means the volume is expected to increase by that number for each additional inch it earns starting at 4. So going from 4 inches to 5 inches, we would expect whatever the volume is at 4 inches to be 201.1 bigger at 5 inches. That's literally what that inches cubed per additional inch means. So in the context of this problem that you were just asked to look at, you were told that the derivative is this function here. And so the derivative at 500 you were given is $15. The units, so this is dCdx. The units for this are cost per item produced. Okay, so what does this 15 mean? Well, this is a cost per item produced when the number of items is 500. So if you think of it in the context that we thought of the problem in Wednesday's class, it's the same idea. If we go from 500 items produced to 501 items produced, then the number 15, the derivative here, tells me that whatever my cost was at 500, I can expect that cost to increase by 15. Now understand that this is just an approximation. To see that, the actual cost function here would be 5x plus 0.01x squared. Now I know you aren't given that information, and on purpose. You weren't given the cost function on purpose. That way you would have to just think about what the derivative means rather than actually calculate this thing. But this would be the cost function, and let me see here. If I go into Desmos and I evaluate this function, so c of x equals 5x plus 0.01x squared. and I look at C of 500, and then I compare it to C of 501. You see, it's approximately 15, right? You go from 500 to one more item produced should add approximately $15. Like I said, it's an approximation. It's not perfect, but that's what the derivative is telling you. The derivative is telling you, and this is for the entire course, the derivative will always tell you the expected increase or decrease in a quantity if the independent variable, which is usually X or T for us, if the independent variable changes by 1, what is the expected increase or decrease of the dependent variable, the variable that it depends on? So understand, so what we just found out was C of 500 so C of 500 was 5,000, and C of 501 is $5,015.01. So the approximate increase this is approximately dC dx. Oh, y'all can't see that, can you? Sorry, wrote all that up on the screen without you seeing it. So the approximate increase or the difference in the change between those two quantities, $15.01, that's approximately the derivative at 500. Does that make sense? Do y'all have any questions about that? Because it really is going to be a big topic for the course that we can interpret what the derivative is telling us for a given problem.
I'm still confused because like on B, on the problem, it just says the cost of producing an item is $15. Wouldn't it be $15 more than the previous?
Right, but it says the approximate cost of producing a 501st, right? So you can read that as saying the approximate cost of producing one more item is $15.
Okay, I got you.
Right, because it's in context here, right? You're talking about the derivative at a production rate of 500 items.
Oh, okay. Yeah, that makes sense.
The derivative, because it says C prime at 500, right?
Uh-huh.
So if I was to look at C prime at a different number, I would get a different derivative. Like
Okay.
C prime at 200. Well, let me just ask you this. Would you expect the derivative at 200 to be bigger or smaller for this problem?
Probably would be smaller.
Well, think about how production costs work in a factory type environment. The reason that factories were so important to the Industrial Revolution is they gave people the ability to mass produce at a smaller cost per item the more items you produced, right? So the more items you produced, the more the costs went down. So the costs get smaller the larger number of items being produced.
Okay.
So we would expect the derivative of this to be larger at say 200 because you're producing you're producing fewer items. So you would expect that the price per item to produce at that point would be larger. But
okay.
The more items you
Yeah,
produce,
I was thinking it said like, sorry, I was thinking it was saying like producing the 500 first item. So that's where I was confused.
Well, I mean that it's saying the same thing. Like producing, if you're at 500, then if you say $15 to produce one more item, that's the same as saying $15 to produce the 501st item because that is the next item. So that's the expected cost increase for producing one more item.
Okay. Gotcha.
And none of the others are correct here. I'm fairly certain you have a couple of questions like this on the homework, so you'll get some more practice at it. But if you just always think of the derivative as being a local approximation, it's basically telling you what to expect the value to increase or decrease by locally, meaning the next one. So from where it is to the next one, then that's probably the easiest way to get through this. I know you have a skills quiz as well, where there's a question like this asked for next week's skills quiz. All right, any other questions on this problem? All right, well, let's take a look at a new concept for us in the course, something called differentiability. We've calculated derivatives using the limit definition of the derivative, so we know how to calculate them. The question that we want to ask at this point, and it's a good question to ask, because we'll see what kind of answer it has. The question that we want to ask at this point in the course is, are there some places / functions where we cannot calculate the derivative? And this is if you were developing this topic for the first time, this is a question that you would immediately ask yourself. And the reason that you would ask yourself this question is we've already seen that when the limit of a function doesn't exist at a point, we've already seen that that means that the function is discontinuous at that point. So now we're in a context where the derivative is a limit, right? I mean, we've been calculating it as a limit. The derivative is a limit. What if that limit doesn't exist? What happens then? Okay, so it's an obvious question for us to ask, and there is an obvious function for us to look at as an example of what happens, and that is the absolute value function. So as an example of this, let's just consider real quick, if you have the absolute value function, we know what this function looks like. So here's what I want you to imagine for a second. The derivative of a function is the slope, right? It gives you a direction to head in. So we equate derivatives on a graph with slopes, or you can think of them as kind of like you're walking along a street. It's kind of like street signs. So if you're walking along a function, the derivative is the street sign telling you which direction to head in at any point. So imagine your journey along this graph. You start out over here, you're walking along the graph, and as you're walking along the graph, everything's pointing you in the same direction, right? Reading from left to right. You're walking along this line, the arrow isn't changing. But what happens when you get to 0? Well, when you get to 0, here's how I think about it. If you get to 0, well, you can keep following the direction that you were going. So that's the direction that you were going in. But you notice that there's another path to take off to your left, which is, in this case, a 90-degree angle to the one you're on. So it's kind of a fork in the road, if you will. So you could follow this choice. So this is your first choice, to keep going in the direction the graph is telling you to, or you can go along this path. And see, that's problematic, because we would like to say that at any point on the graph, at any point where you're walking, there's only ever one direction to head in, but that's clearly not true at 0. Because if you get to 0, everything up until that point is telling you to keep going in this direction. But the actual graph itself is saying, no, you need to come down this way. So that difference in the path that you could take at that point is very problematic mathematically. In fact, it's something that's known as a point of non-differentiability. It's a point where you can't take the derivative at. And I'll prove that to you here with a limit calculation real quick. But at this point, f prime of x does not exist. So we say that the function f of x is not differentiable at the point x equal to 0 in this case. You can't take the derivative at a point where you have two different directions to go in simultaneously. So let me sort of prove to you that that's a bad point. All right, I want to calculate or try to calculate the derivative of this function at 0. Well, we know from our limit definition in class that f prime of 0 would be the limit as h goes to 0, f of 0 plus h minus f of 0 over h. So that's the limit definition of the derivative. All right, our function for this exercise is the square root. So 0 plus h is 0 plus h inside the square root. So this would be 0 plus h, or not square root, absolute value, excuse me, would be 0 plus h inside the absolute value minus 0 inside the absolute value divided by h. But here's the thing. 0 plus h is just h, and the absolute value of h, since h could be approaching 0 from the left and right, in fact it is, right, because it's a two-sided limit, I need to leave that absolute value on for now. And then the absolute value of 0 is just 0, so what you get is you get the absolute value of h divided by h. So we talked about how to handle limits that involve absolute values. You have to look at the limit from the left and the limit from the right because the absolute value function changes. So if you look at the limit as h approaches 0 from the left, so if you're on this graph and you're approaching 0 from the left, you're on this function, and this function is not h, that's the function h, it's negative h, it's the one that has negative slope. So the absolute value of h for negative numbers is defined to be negative h over h, which would be negative 1. So your slope on this part of the graph is negative 1. Compare that with approaching h from the right. So if you look at the limit as h approaches 0 from the right, the function over here is just y equal x. So when evaluated at h, the absolute value of a number that's positive is just that number. So the absolute value of a positive number is just positive. You get h over h, which is 1. So the slope on this side is 1. Hence we had different directions, right? You got a slope that's negative on one side, a slope that's positive on the other side. But now think about what this says in terms of what we know in the course already about limits. If you have a limit from the left at a point that's different than the limit from a right at a point, what do we know about that limit? Feel free to say something if you want. If the limit from the left is different than the limit from the right, what do we know?
Does not exist.
Does not exist. So this says because they are not equal, this limit does not exist. But this is the limit that we would use to calculate the derivative. So this is in essence saying the derivative does not exist because the derivative is a limit. So this is saying the derivative does not exist at this point. Now here's the thing. If I tried to calculate this at any other point, it would work just fine. Like imagine trying to do f prime of 2. You're over here at 2. Well, the limit from the left would be 1 and the limit from the right would be 1 because the slopes are 1 over here at 2. If you're over at -5, the limit from the left would be -1 and the limit from the right would be -1 for this derivative because the slopes to the left and right are the same. But only here at 0 are the slopes to the left and the right different at that point. So what we have to wrestle with for this topic is, when are we going to run into this problem again? I would like to know, without having to do this limit calculation, that I'm going to have a point that I can't take the derivative of. So this is one of those things that's highlighted on your exam review that you need to memorize, and it's a list of where functions are where you cannot take derivatives. So places where the function will not be differentiable. So there's 3 of them that we're going to talk about, but I want to see if, based on what you've seen so far, you can answer this follow-up question. So the definition that we've gotten together right now is a function is differentiable at a point if the derivative at that point exists. It's differentiable on an open interval if every point in the interval is differentiable. So differentiability, like continuity, is a point-by-point property. You're either differentiable at a point or you're not. If you're differentiable at every point inside an interval, then you're differentiable on that interval. Same way that continuity worked. So the example that we just looked at, so let me throw it up here to remind you once again, the example we just looked at, this function is continuous, right? Like there are no breaks in the graph. The function is continuous, but yet there was a point here where the derivative didn't exist. So even though the graph is continuous at 0, you can't take the derivative there. So we've already seen an example of where continuity at a point doesn't guarantee differentiability. So just because you're continuous at that point doesn't mean you're necessarily differentiable at that point. And so the question I'm asking you here is, does that still hold if we turn it around? So if we reverse the implication here and I say differentiability at a point, and then blank continuity at a point, what should go in the blank? That's what I'm asking. Should it be differentiability at a point doesn't guarantee, just like this statement, or should it be differentiability at a point does guarantee continuity? In other words, how does it work? So that's the question that you're being asked here. The question you're being asked is, are there functions that are not continuous but still differentiable at a point? So what do you think? All right, all of you have answered. Turns out this can never happen. You cannot have differentiability without continuity. It's required. Okay, so this leads to a really important result in the course. And we're going to actually prove this result together this morning. But just to update your notes, differentiability at a point guarantees that you have continuity at a point. You can't take the derivative unless you're continuous. But just because you're continuous doesn't mean the derivative has to exist at that point. Here's the theorem that you need to memorize. The theorem says if f of x is differentiable, meaning I can take the derivative, f prime at a exists at the point x equal to a, then the function f of x is continuous at the point x equal to a. So this is oftentimes referred to as the differentiability implies continuity theorem. But you can't reverse it. What I mean by that is you can't say continuity must imply differentiability, because it doesn't. The square root function is an example where it doesn't. So differentiability must imply continuity, but continuity at a point doesn't necessarily imply differentiability. So the follow-up question to this is when is, maybe I'll say it better this way. At what points x equal to a does f prime of a not exist? In other words, at what points on a graph would we expect to not be able to calculate the derivative? So this is a list. The first one you've already seen. So the example that we just looked at here is where the derivative from the left doesn't match the derivative from the right. Whenever that occurs, you get a corner. So these are called corner points. Okay. So x equal to a is a corner. So any corner point, go ahead.
And the corner would only show up on the f of x, but f prime at x, it would just be like a hole, basically, right?
No, the corner refers to the fact that there's a sharp turn in the graph, not the point. The point itself is there, right? The point exists. This graph is continuous, just like the absolute value. It's just the graph makes a sudden change in direction.
And you're talking about the graph of the f of a, or f of x, not the prime graph, right?
That is correct. That is
Okay.
correct. I'm talking about the original function. We've yet to, in this course, plot a derivative function. We're going to do that on Monday's class. So yeah, I'm talking about the original function. So if the original function has a corner in it, you can't calculate the derivative at the corner point. You can calculate it anywhere else, but you can't calculate it at the corner point.
Okay.
Now, there's something that's slightly related to the concept of a corner, and I don't write this as a different thing. It's an old word, but it is technically slightly different. It's called a cusp point. So a cusp at A would look like this. The graph bends into the point, and then it bends away from the point. Those are slightly different because here it's coming in at straight lines to create a corner. Here it's bending into a point to create kind of a, we call it a cusp. So x equal to a is a corner, x equal to a is a cusp. Either one of those two things, if you see something like that on a graph, wherever that point occurs, you cannot take the derivative there. So this is a cusp. Okay, so that's one place where the derivative will not exist on a graph. The second one, we just got through doing an example of it, or just got through talking about it. Another way to write this theorem, have I talked to y'all about something called the contrapositive in class before? I don't remember if I have or not. I don't think I have. Let me put it to you this way. Skip down real quick. If I said, if it's raining, then it's cloudy. That's a true statement, right? We would agree with that statement?
Yes.
Okay. If I reverse the statement, is it still true? So this is the original statement. If I reverse it, it's something that's called the converse. So the converse of this statement, if I reverse it, says if it's cloudy, then it's raining. Is that a true statement in every case?
No.
That is not true in every case. So we say when it comes for the original statement, simply reversing an if-then statement doesn't make it the same. So the converse isn't the same. However, if I reverse and negate, it is the same. It's something called the contrapositive. So let me show you an example of that. So reverse, take the original statement, reverse it, and negate it. So reversing it, you would say if it's not cloudy, you have to negate it, then it's not raining. Is that a true statement? If it's not cloudy, then it's not raining. Is that a true statement?
Yeah.
Yeah. So the original statement and the contrapositive statement are the same. So what's the contrapositive statement to this theorem? Reverse it and negate it. What would it say?
If f of x is not continuous at x equals a, then f of x is not differentiable at x equals a.
That is correct. So we're making a list here of all the different places where a graph can fail to have a derivative. What does this just tell me? What is a place where a graph can fail to have a derivative?
At a.
Well, assuming where the, yeah, what Colby said, where the graph isn't continuous. This says if your function isn't continuous at a point, then you can't take the derivative at that point. So if I'm looking for places where the derivative doesn't exist, if x equal to a is discontinuous, then I can't take the derivative there. So we had a list earlier in the course of places where graphs were discontinuous. These were things like any jumps, any vertical asymptotes, any of these removable singularities or removable discontinuities, right? So all of those are places I can't take derivatives at. If your graph has any one of those, we're out of luck. You're not going to be able to do the derivative. All right, and the third one is kind of a weird one. X equal to A has a vertical tangent. Vertical tangent. Now, this is, like I said, this is a weird one, but it does happen quite a bit. If you want to think of it in terms of what the slope is telling you, the slope becomes infinite. So any place where the slope becomes infinite, we can't take the derivative at such a point. The way that the graph of that would look kind of like this. Say you've got the function x equal to a. You've got a graph that comes along here, and it turns very sharply at the point A. And then right at the moment it hits x equal to a, it becomes infinite, and then it kind of tapers back off. So this is an example of a graph that has a vertical tangent. The slope of the tangent line at that point is infinity. An example of that function, of a function that does that, is say the cube root of x at x equal to 0. If you were to graph the cube root function at x equal to 0, it doesn't have a derivative at 0 because the derivative is infinitely large. So this list is something that you're going to be held accountable for on the exam. You need to memorize these 3 possibilities. For this course, these are the 3 possible places where we can't take derivatives. At corners or cusps, any place the derivative is discontinuous, or anywhere place the function is discontinuous, excuse me. Maybe I should say that x equal a is discontinuous for f of x. X equal to a is a corner for f of x. So anywhere the function has a corner or the function has a discontinuity, x equal to a has a vertical tangent of the function f of x. We're always talking about the original function here. All right. Are there any questions there?
I understand a hole is discontinuous, but why couldn't you take the the derivative of it since it's a limit? You get what I mean?
Sure. It comes back to this theorem. So if you believe this theorem is true, then any place the function isn't continuous, then the function can't be differentiated. Now there's a proof of this result in your textbook that I would encourage you to read. It's not particularly long and it is kind of interesting. But in terms of the whole example, let's just think of it the way I thought of the walking along for the absolute value. So you've got a hole here at x equal to a. You're walking along and you get to the edge of this hole and it tells you that you should keep going, but there's no direction if you're actually on the hole. So say you take one step off, it tells you to take a step onto the hole. You're at the hole. Where does the hole tell you to go?
Nowhere.
It doesn't give you a direction. So to say that you can compute a derivative at a point is akin to saying that you have to be able to give me a specific one direction to head in, one unique direction to head in at that point. And even though the limit tells us to step onto the hole, once you're on the hole itself, it doesn't tell me where to go next. There's no unique direction there because there's no function value there. So there can't be a slope there.
That makes sense.
CJ, to answer your question, you will need to be able to list these out. It won't necessarily be multiple choice. So you will need to be able to list them out. All right. So let's see if y'all are kind of understanding this concept. And here's a question kind of follow up with. So I have a piecewise function here, and I want to determine all of the different points at which this function is not differentiable. So at which of these values can I not take the derivative? All right, I'll let y'all think about it for a second. So as you're answering this function, I've told you the derivative of 1 over 5 minus x, if that helps you, which it should. We'll talk about that here in a second. Can y'all see this question okay? Because nobody's answered yet. Oh, there they are. I think it was just slow in updating.
It's just different trying to figure out think of it, the derivative of a constant, kind of like adding an extra layer. So just in my case, that's why it's taking.
Yeah, no, I know this problem's different. Like we haven't done anything like this so far this year. It's kind of like what we did with continuity, but it's a little bit different. So just keep that list in the back of your mind. Think, is there a corner or a cusp happening here? A corner happens where your derivative from the left doesn't match your derivative from the right. So your signs change. Your signposts change. You're heading in one direction coming from one way, and you head another direction going in another way. Think also, is there any points where the graph isn't continuous? Because if it's not continuous, you can't calculate the derivative. And then finally say, is there any place my derivative might become infinite? If my derivative becomes infinite, I can't take the derivative there. All right, we're about to run out of time, so let me jump in it with you. And as we're going through this, go ahead and enter answers. Keep thinking about it. So looking at the different points that are on your list, we'll start with x equal to -1. If you look at -1, is there anything bad happening at -1? No, it's just the graph of 0 at -1. It's just a constant graph. There's no issues there. So that one is so f prime of -1 exists, right? That one's fine. It's not a value to be worried about. What about x equal to 0? Well, if you look at x equal to 0, we switch between this graph and this graph. So let me think about the derivatives here real quick. If I was to write down the derivatives, the derivative of 0 is just going to be 0 because that's its slope. the derivative of 5 minus x is a linear function. Its slope is -1. And then you were just told that this function has a derivative of 1 over 5 minus x squared. And so this is for x greater than or equal to 4. So these are the derivatives associated. And if you look at 0, you change from having a derivative of 0 to having a derivative of -1. So here you're heading in a constant manner, and then you drop down and start moving. So you go from 0 to -1 for your slope. That creates a corner. So you have a corner at x equal to 0. Similarly, if you looked at x equal to 1, if you looked at x equal to 1, 1 is between 0 and 4. This is a linear function. It has slope -1. There's no issues there. So the derivative at 1 exists. What about x equal to 3? X equal to 3 is on that same linear function. There's no issues with derivatives on a linear function. They have a single slope the entire time. So f prime at 3 also exists. Yes, Kobe, to answer your question, the function is not continuous at 0. So that's another way. I just wanted to show you it has different derivatives there as well. But you're correct. If you look at f at 0, it's 0. And if you look at f of 0 from the right, it's 5. So you would have a jump discontinuity at 0. So the function isn't continuous. You have a corner at x equal to 0, and f of x is discontinuous there. So by any measure, f prime at 0 does not exist. Okay, x equal to 4, real quick. I know I'm a minute or two over. X equal to 4, if you look, 4 is the point where we break over between the two functions. So if I plug 4 into this function, I get 1. If I plug 4 into this function, I also get 1. So here, f at 4 is continuous. They match at 4, the function does. But let's look at the derivatives. The derivative to the left is -1, and if I plug 4 into this derivative, it's just 1. So the derivative as I approach 4 from the left is -1, but the derivative as I approach 4 from the right is +1. These don't match. So that would say that f prime at 4 does not exist. And finally, if you look at x equal to 5, what's wrong with x equal to 5?
It'd give you a 0 in the denominator.
Which means it's a vertical asymptote, right? So x equal to 5 is a vertical asymptote, which means the function isn't continuous at 5. And if the function isn't continuous at a point, then it's not differentiable at a point. So x equal to 5, f of 5 is not continuous, which automatically means that f prime at 5 does not exist. Now, you're probably going to want to come back and review this question because I know I went through it kind of fast, but you need to be able to, just like we did for continuity, determine limits from the left and right at points. You need to be able to determine derivatives from the left and right at points, and be able to determine things like whether or not the derivative exists, keeping in mind that list of things that we talked about. All right, that's a good stopping place for today. We will concentrate all of our efforts on Monday for graphing derivatives. We're going to talk about what the derivative graph looks like and what the derivative tells us about a graph on Monday. So a lot of graphs, a lot of questions to respond to on Monday. All right, y'all have a good weekend.
Sir, could you
Yes.
could you hit OK on the response so we can get points for the learning catalytics?
Yeah, sure.
Okay, thank you.
All right, y'all have a good weekend.
You too, sir.